We're happy to have Sam van Leuven tell us about 4D modularity.
Okay, thanks to Vishnu and Supra for organizing the conference, bringing us together, and also to the participants and the folks getting so far. I'll be talking about 4D modularity. I'll explain what I mean by that. Many of you, in the previous 2 editions of this workshop, I've been giving talks on a similar topic, so many of you probably already know a little bit what I mean by that. But I hope to present you something new. So just to get everyone on the same page, I hope I won't bore you because I think I always have this slide like this, but I just want to quickly review what we mean by modularity in 2-dimensional CFT. So in 2D CFT, we have a state operator correspondence, and we can calculate the thermal partition function of this theory, where the Boltzmann weight is given by, the Hamiltonian is given by the operator dimension, such. And we can additionally weigh this by the momentum of the state along the S1. And if we calculate, the thermal partition function in 2-dimensional CFT can be equivalently computed as a path integral on a torus, where the parameters in the partition function map onto the complex structure modulus of the torus. Now, what is special to 2D CFTs is that this partition function is invariant under this SLPZ, or modular group, which acts in a projective manner on the complex structure modulus of the torus. This equality just illustrates the fact that we can choose different fundamental parallelograms to parameterize the torus, and the fact that the CFT has scale invariance, which means that it only depends on the complex structure modulus of the torus. Okay, now there's a famous application of this, which we also talked a little bit about during Ashok's which is the following. So the S transformation, which looks like this, so this is a specific SL2Z transformation, you see it inverts this parameter tau. And that actually means that it relates low temperatures to high temperatures, so partition function at low temperatures to high temperatures. This transformation corresponds to sort of exchanging the spatial cycle with the thermal temporal cycle. And using this equality, we can find a universal density of states at high energy that is only controlled by the central charge. Okay? Why that is so is because the low temperature behavior of the partition function is controlled by the Casimir energy of the CFT, which in turn is controlled by the central charge. And because of this equivalence, that also means that the high temperature partition function becomes universal. And that is, of course, a famous result by Hardy. And one finds for the entropy of these high energy states, in general to the CFTs, the following simple formula. Okay. So there are many, so this was made possibly the first application of modularity to dimensional CFT, but there are many, many other applications. In particular, also in string theory, it played a role in originally finding microscopically accounting for black hole entropy in string theory in the Stomach-Lefava story, but that developed into much more. Modularity also plays a key role in understanding how to perform, setting basically a target for how to perform a full quantum gravitational path, at least in supersymmetric systems. Okay, so these are many applications in physics, but of course in mathematics, modular forms play a central role, and they appear in many, many subfields, and they actually relate certain subfields in interesting ways. So that's a very, very central both in theoretical physics and okay. Now, one might ask the question whether, or what one might expect perhaps, that CFT data in dimensions greater than 2 could be universal at high energies as well. And then as sort of a sub-question, one might ask whether modularity, that is such a simple tool in 2D CFT, generalizes to high dimensions. Okay? But if we try to follow through the same arguments, right, in this case we're looking at local operators on RD, which correspond to states on a D-1 sphere. If we sort of naively try to run through the same argument for the thermal partition function, say, we find that there's no symmetry anymore in D greater than 2 between the spatial geometry and the temporal geometry, and so it's not obvious how to generalize these arguments. Now, nonetheless, there have been sort of, over the years, there have been proposed various tools. So actually, very early on, already in 91, Cardy observed that there is actually a kind of modularity for, at least for free conformity coupled fields. That's a bit more mysterious. He didn't fully explain it, he just observed it. Okay? People also have tried to use alias CFT to address questions like this. You can also try and change the geometric background to explicitly include a torus, in which case you would have an SL2C group, but then there's no, you sort of lose the state operator correspondence. You lose the connection with the local operator data. And perhaps most recently, there has been some work that addresses this question based on the concept of the thermal effective action that is also somehow a generalization. Yeah, you can view as a generalization of the concept of modularity in 2 dimensions. All right. Okay, so this is sort of the general background. Now, in superconformal field theories, one actually over the past 2 decades or so, one actually has access to exact expressions for supersymmetric partition functions on a variety of geometric backgrounds. And in this case, we have the expression, and we can just inspect the inspection to see what kind of properties it has. And indeed, sort of there's unexpected signs of modularity in a whole host of supersymmetric partition functions, including these indices, which I'll define in a moment, but which are rather close, at least in the definition, to what a thermal partition function is. Okay. So, in addition, so apart from the fact that these exactly calculated quantities show these signatures of modularity, there's also been, like in 2D, there's also been some interesting applications of these modular symmetries in holography. Okay? So it seems that there is an interesting analogy. But so far, the physics and the geometry of this SL2Z action is not so clear. It's not, I would say it's not fully understood.
What is SL2Z action?
That's, I'm going to get to. Yeah. Okay. So the motivation for my talk is to focus on a specific quantity, namely the 4D n equal to 1 superconformal index. I'll define it in a moment. And I want to try and convince you, or give you a bottom-up argument for a type of modular property that it satisfies. Okay? My playground is going to be the simplest possible theory, the supersymmetric analog of a free scalar, the free chiral multiplet, but at the end, I'll indicate how this can generalize, how these arguments could generalize to non-trivial CFTs and also to other dimensions. Okay, so maybe before I continue, let me check if there's any questions about the general motivation.
There's 2 types of modularity we spoke about. There's the one that Edgar and others describe which have no acyclic variability, just a
Yeah, that's the thermal effect reaction.
Yeah. So this is a completely different type of modularity.
Yeah, I would say. Although, yeah, so actually, I probably won't come to that at all, but if you look at this thermal effect of action for free firmly coupled scalars, there is actually a closer analogy between the two methods. And that's also related to these observations by Cardi who were happening. Okay. So what is this performance index? So it's defined in the following way. So it's defined for general n equal to 1 SCFPs. It's defined rather similar to a thermal partition function in that we quantize our theory on a free sphere, okay, and we weigh it by this Boltzmann factor, where delta now is not quite the usual Hamiltonian. It's some anti-commutator of supercharge. It's supercharge and supernormal charge that can be expressed in terms of the bosonic charges, the scaling dimension, and the two independent angular momentum is as free in the following way. So R here is the generator of the R signal. Okay, so that part is similar to the thermal partition function up to this sort of supersymmetric Hamiltonian, but we include some other factors as well. We include the -1 to the F, familiar from the Witten index, which weighs fermions with a minus sign. And then we additionally weigh states by these combinations of their charges. Okay? So here, by the way, I wrote the index as a function of these chemical potentials which are related to these fugacities. Okay. So by construction, this object only receives contributions from BPS states, or supersymmetric states, in this Hilbert space, namely those that are annihilated by this supercharged cube. Okay, so those states satisfy a charge relation with where these charges here are related through the fact that their delta is zero. Okay, this also implies that the index is a protected quantity, and that means that it's exactly calculable for many non-trivial CFTs because we can calculate at the free point of the theory, and then but this result holds for turning on the value. All right. So as I said, I'll mostly focus on the chiral multiplet, so let me just review the index of the chiral multiplet in some detail. So what is a chiral multiplet? It's a complex scalar field in a wild fermion. Okay? And so we want to consider, to calculate its index, we want to consider operators, we consider supersymmetric operators, namely those operators that satisfy this charge constraint. Okay? Then, through the operator state correspondence, we can construct the Hilbert space. So we first construct a single letter Hilbert space consisting of just one field operator and an arbitrary number of these so-called BPS derivatives. Okay, so these are this component of the Weil spinner and this complex scalar field, and these two derivatives all have this condition, all satisfy this condition, and those are the only ones that satisfy this condition. Okay, so that's our sort of single letter Hilbert space, and then the full supersymmetric Hilbert space can be constructed by considering all the works that can be made out of this.
So this works, of course, because the index is protected, so you can compute it in the free theory.
Yes.
So earlier you said something about Cardi and modularity and something which worked for free theories, which I did. So is this also going to be some version of that, something that will work secretly for free theories, or?
Yeah. I think that's not entirely clear, but yeah, I think probably the notion of modularity in 4 dimensions is sort of related ultimately to this free field. Okay. To be honest, to be honest, I don't really know the answer to that. But well, the reason I'm saying that is because many of these modular properties depend on these very special functions with, integer powers of the
This is the index, right? This is to do with the fact that it's an index.
Yeah, this has to do with the fact that
Not that the theory is free.
no, exactly.
Theory
So
is not free, but
that's
this index is the same as the free theory. So
Yeah.
the index doesn't care if the theory is free.
Well, it cares. I mean, gauge theory indices are different from the.
I mean, this index is just protected.
Yeah.
So
In the year, you need, I mean, by non-free having a gauge theory. So the coupling could be arbitrarily small.
yeah.
that you mean you impose a Gauss law?
Yeah.
That okay, but that
Yeah, that makes things a little bit more non-trivial, but it's still sort of.
And there are indices of theories available which do not even have invariant distribution. In which case you cannot call them free, but indices exist.
Yeah.
and
But in
For
the end,
that you need some roundabout.
although in the end they might be related, there's probably some free field description. Even
No, I
if it's-
doubt it. Because it's not free, right? I mean, this is a fixed point of the conform manifold.
Yeah.
For example, E6 Milan-Mushansky theory.
Yeah.
You might try to find a theory description which is free but close to this.
so but will
Yeah,
there be the
that's what
modularity
I
problem?
mean.
Will there be the modularity problem?
So that requires, I mean, there are
We're
various
gonna-
types of modularity.
We're
we
gonna,
can talk
so I'm
about.
gonna explain how this works in the context of the free power model. If sort of time permits, I'll tell you how this extends to H. All right. Okay. So once we've constructed this Hilbert space explicitly, you can just perform the trace. Okay. Now there's actually a trick to perform this trace quickly. So we only have to perform the trace of this single letter Hilbert space. Okay. That gives us something like this. So these two denominators are related to these arbitrary derivatives. So the two terms in the numerator correspond to the two letters. And if we do this operation of statistic exponentiation, that precisely gives us the trace of the full Hilbert space. That's just the mathematical trick. Okay? And the result of this can be rewritten as a special function, which is known as the elliptic gamma function. So the elliptic gamma function can be written in this way. You can write it as this double infinite product, okay, where it's again p, q, and y are related to z sigma tau for this exponential. Okay. Now I want to calculate this index a little bit differently. Okay? So I want to consider the single letter Hilbert space, but now I want to separate the Hilbert space into two sectors. Okay? Depending on whether I have more d plus dot derivatives or more d plus minus dot derivatives. Okay? So these states will either have their J1 quantum number smaller or larger than the other. Okay? So maybe in a picture it's easiest to understand. So all these single letter states, they fill up this positive quadrant of the J1 thing. Okay? And I'm now just sort of artificially splitting this set into two subsets corresponding to this guy and this guy. Okay? If I do that, then the full Hilbert space will actually can be factorized into states, into words that correspond to letters that are only made up of sort of the positive, of these letters and states that are made of these letters. Okay, so I call these two Hilbert spaces J2 less or equal to 0, greater or equal to 0, where J2 captures the difference between these capital J1 and J2.
The other factor should be J2 greater than 0.
Yeah, so the reason why, so I'm sorry, so the reason why I put this larger equal sign on both sides is because I want to include the J2 less or equal bosons here, but fermions less than. And for the other one, I'm going to include, so, yeah, that's a little bit of a detail, but yeah, sorry about that, the notation. Anyway, but that is in there. Okay, so now I have this factorized Hilbert space. I can perform this trace again. Okay, and I can just use the identity that the trace over two Hilbert space factors becomes the product of traces over the separate factors to get a factorized expression for the index, which again is expressed in terms of this elliptic gamma function. So that's a little bit funny, perhaps, but in fact this expression can be checked to be true. So it is actually a mathematical fact that the elliptic gamma function, which was the original index, can be factorized into two elliptic gamma functions like so. That was known in the mathematical. So now I want to convince you sort of the main part of this talk will be to convince you of these two claims about this state. Okay. So first of all, I'm saying that this factorization cannot only be understood at the level of the Hilbert space, as I've explained, but we can also interpret it geometrically. Okay. So how do we interpret this geometrically? Well, let's first think of the free sphere on which our states live as a Hopf vibration. Okay? So what is a Hopf vibration? Well, a Hopf vibration is some non-trivial circle bundle over a two-sphere, okay, that together makes up my free sphere. So here I've drawn a cartoon where this is the base two-sphere and here is the Hopf fiber, the circle. Okay, but obviously this is a cartoon because this is not a direct product. The topology is not that of S2 plus S1. It is a non-trivial bundle, and so the total geometry is an S2. Okay. But if we restrict S3 to a hemisphere of this base, the vibration trivializes. Okay, that's also well known. So if I just look at S3 as a part of S3, where I either consider the southern hemisphere with the Hopf fiber or the northern hemisphere with the Hopf fiber, I can think of this as a direct product. Okay?
So could you just remind us of the details of that? Because I thought that the radius of the fiber varies as a function of cos theta or something. So if you take...
No, the radius is constant. The radius of the Hopf fiber is constant.
But when you look at the metric, isn't there a cos square theta?
Yeah, but that's not the Hopf fiber. That varies.
Isn't this S1, you write an S2 metric, and then based on where you are on the S2, you also fiber on an S1, and the size of the S1, I mean measured physically, depends on where you are on the S2.
No. I think I know what you're referring to, but that in that case, the circle that is changing. So you can think of this also as a torus vibration, where over an interval. And then cycles of the torus, both cycles of the torus vary as I move across the interval, and actually the interval is indeed the polar angle here. The polar angle here. So as a function of this polar angle, there's these two circles of the torus that indeed both vary with this cos or sine that you mentioned. But the proper Hopf fiber is actually the sort of the combination of these two circles that remains always at a constant size, everywhere across the bases.
Hopf fiber is the great circle.
You can also think of it as a great circle that sort of rotates over S3 depending on where I move over S3. Okay, so that's sort of what we need to know to really state this claim 1 in a bit more detail. So I'm going to claim that at the level of the Hilbert space, these two sectors that I defined, the J2 less or greater than 0, that they can actually be thought of as the Hilbert spaces of a chiral multiplet quantized just on a hemisphere times the Hopf fiber. Okay? So these Hilbert spaces are just, this one is equivalent to this one, and this one is equivalent to that. That's what I'm going to show. Okay? And
So here you are thinking of this split of S3 into two solid tori.
no, yeah, it's basically two solid tori. Yeah.
And then you are associating one piece to this one and the other piece to that one.
Yeah.
But then you have to, but then the actual index is not simply the product, right? You would have to have this S transformation.
That's right. That's what you'll see. There is an effect of S transformation. So let me. So this is just at the level of the Hilbert space. But if I take the trace, so the claim is that these two factors that I showed you can actually be interpreted as what I call hemispheric indices, which I'll properly define a bit later, but this is just to give you the overall picture. Okay? So these factors can actually be interpreted as these hemispheric indices. Hemispheric indices being traces, certain traces over the hemisphere, over the Hilbert space on a hemisphere times a circle. Okay.
So you
And
have
the
a
wave
state
function-
operator maps?
The wave function has to satisfy some boundary condition at that place at that loop.
That's right. That's
So that doesn't change
So-
the product structure.
that doesn't change. So yeah, I'll talk about these boundary conditions in detail. So there's actually two types of boundary conditions that you can put that preserve supersymmetry, and for both of them, you get a factorized product like this. I'm going to focus on what I'm going to call the plus boundary condition. So that's this label plus here, but it would also work for the other type.
So as you explained at the beginning, this index you really compute by looking at primary operators in R4 and using the state operator map to say they're the same as states in S3. In this
Yeah.
hemisphere, is there a similar state operator map you can use?
No, there's no state operator map, but I can just directly quantize the chiral multiplet on this path, and that's what I'm going to do.
I see.
So in this case, there's no connection with the local operators directly. Maybe indirectly through the fact that they combine into the total index, but yeah, you can just separately do this quantization. Okay, and then yeah, to Abhijit's question. So when I actually calculate the traces, the fact that this Hopf vibration is non-trivial is reflected in the fact that the way these traces are weighted is actually by sort of different charges. So for the southern hemisphere, I will weigh it by some operator J1, which would correspond to rotations in the southern hemisphere, and J2, which corresponds to rotations around this circle. But for the other hemisphere, because the vibration is non-trivial, I find that there's a different rotation charge by which I must weigh the trace. Okay? I'll get to it. That's a bit of detail. I hope that the main statement is clear, and I hope that it's clear. Okay, so that's the detailed claim one. But now, of course, I was talking about modularity. So far, there has not been any modularity, so let me now make my claim two. Okay? So the idea is that this trivial vibration allows me to do just a standard KK reduction. So I first factorize my Hilbert space into these two Hilbert spaces defined on hemispheres times circles. And now I can imagine that I KK reduce the Hilbert space on the hemisphere, just because it's a direct cut. I can just do the reduction. And I will get this infinite product, so corresponding to the various KK modes, of two-dimensional Hilbert spaces. Okay? But there's two of them because I have to factorize into hemispheres. Okay? This expression, this fact, that I can view the four-dimensional supersymmetric Hilbert space in this sort of two-dimensional sense. In particular, we'll realize the four-dimensional index is some infinite product of two-dimensional indices, which I'm going to write like this. So remember, here I'm using the fact that the index can be thought of as a path integral on S3 plus S1. So that's this side of the story. And then on this side of the story, I can think of the two-dimensional indices as partition functions on the tori. Okay, and this is T2 of tau and T2 of sigma are respectively the tora comprised of the Hopf fiber and the temporal circle on either southern or northern hemisphere. Okay, so I'm getting this thing allows me to find some expression like this. And now it will turn out. So the torus is coming in from the fact that when I calculate the trace over these separate factors, right, I think of that as a partition function of the torus, which is comprised of the temporal circle times this Hopf fiber.
So what you're saying is there's an S1 in the vibration.
There's an S, yeah.
There's an S1, and then there is also the temporal circle, which also should have been there in S3 cross S1. I guess it should have been there.
Yeah, so that's this guy.
I see. So that's okay. So that I see. So and you
This is at the level of the Hilbert space, and now I'm interpreting this as a path integral with a temporal
I
space.
see. And the S2 is not going to play any role in this modularity. There was also an S which is not in the hemisphere. The hemisphere will not play any role in the modularity.
I mean, it plays a role in the sense that it's sort of that we not get a simple dimensional reduction to a single 2D theory, but it's this whole product that's sort of related to the fact.
I see. So when you do dimensional reduction, you do it on the hemisphere, not on the
Do it on the hemisphere.
Yeah, that's what I was looking at. So that's not the standard conceptual reduction, right?
No.
Usually you do in the center.
Yeah, sorry. So maybe I'm using the wrong. I'm reducing on the hemisphere. That's what I mean.
So then all these questions about boundary conditions, etc.
That is all important. This is going to depend on the boundary.
But maybe that the fact that M here is the same as M there is about one boundary condition.
These two M's.
Those M's are the KK modes, right? The fact that they're the same on the left and the right is probably already a
Yeah, so the fact that it's only labeled by one integer has to do with supersymmetry, because really you should get some spherical harmonics, but it turns out it only. Anyway, I'm going to get.
So what do you tell the same is the product? It's not a direct sum.
Yeah, it's just the product, so that's not really.
You can order it any way you want.
No, it's a product.
So what do you do product?
Oh, sir. Okay, sir. We can tell you question.
So which is the circle you're reducing on for the hemisphere? Is it the...
No, I'm reducing on the entire thing, so the full.
is you're replacing it with spherical harmonics?
Exactly.
So you're doing a
Yeah,
spherical
there are some details there. Have to do with supersymmetry and whatnot, but that's roughly the idea.
So, why didn't you get a direct sum? When you do the KK reduction, the Hilbert space will become a direct sum. Or maybe the modes will become a direct sum, but you're saying the
I'm
space
talking
will be
about
direct.
Fox
I see.
space.
Yeah.
When I said
Sorry.
Hilbert space.
Yeah, the modes are sums, but you're taking the Fox space.
Yeah, I'm sorry. Yeah, I use multi-letter.
Thank you.
Sorry. Okay. Any other questions?
Is understanding why we can indicate as a physical variance?
No, that's not entirely obvious. Okay, but I can ultimately prove it. But this is sort of the picture behind it. So there is somehow, and it's a bit surprising, and there's some subtle details here. But
You're counting something on that final torus,
yeah,
but it's not obviously that what you're counting is something about a form of influence with respect to it. It's a physical variance, not every future and torus.
well, this will be indices of sort of. I mean, the effective two-dimensional theory that I'm getting is actually okay. Sorry, so maybe I'm confusing with the KK terminology.
Yeah, I'm not sure about the KK. I'm just saying at the end you're reducing it to torus partition.
Yeah.
But of what theory?
Yeah. So these will be of some two-dimensional CFT. It's sort of trivial. We'll get to it. Yeah.
CFT or unit mass, right?
Sorry. Yeah, that's my terminology. I'm sorry. I'm using confusing terminology. So it turns out that only the zero modes of the spherical harmonics, but it's really monopole harmonics. There's some monopole background. And it's going to be only the zero modes that contribute, but it turns out that there's an infinite number of zero modes. So they are actually all masses. So maybe, I'm sorry, I have to figure out maybe a better terminology there, but they are all masses.
Yeah, there's no confusion because we have
No, they're all masses. They're all zero. That's basically why they're only labeled like one number, as opposed to two for the normals.
And will you have modular invariance for each M separately or alternatively?
Yeah, that's a good question. I'll get to that at the end, but you don't have the nicest modular property is only for the product, not for any phi sub, not for the phi sub. Only the product has a nice modular. Okay, so the idea is that this will be sort of the bottom of derivation of what we call modular factorization, sort of a wider point. So this is the physics. Okay, so let me see how I'm doing with time, and then try to fill you in on some. So let me try to fill in details as much as I can. So the remaining plan is to actually do this quantization very quickly and define what I mean by this hemisphere index, and then come to the statement of forming modularity. Okay, so we already discussed in some of the questions. We're going to quantize the four-dimensional chiral multiplet on a hemisphere times a circle. And to preserve supersymmetry, we have to do this in a non-trivial R-symmetry background. This was studied in detail in this paper here in the context of the full sphere. And I can use many of their results for the hemisphere as well. Okay, so yeah, I'm really relying heavily on this paper. Turns out that the supersymmetric sector of this theory reduces to short multiplets of a 2D 0,2 supersymmetry algebra. Okay? And which multiplet depends on the boundary condition that I put. So there's two types of boundary conditions, which are called D and R, referring to, doesn't really matter too much what they refer to. D refers to Dirichlet, R refers to Leuven. But in any case, if I impose the Dirichlet condition on my scalar, the supersymmetrized condition of the fermion, then I only get what are known as Fermi multiplets of 0,2 supersymmetry. What is a Fermi multiplet? Well, that just consists of a single left-moving complex Fermi. Okay? If instead I impose a Robin boundary condition on the scalar and a supersymmetrized version of the fermion, I get these 2D chiral multiplets. Okay? 2D chiral multiplets, which consist of a complex boson, which I call rho here, and then a right-moving 2D fermion. Okay, so what are the other things here? M labels the J3 eigenvalue. Yes, sorry. Perhaps what I didn't say here is that so the supersymmetric sector corresponds to the zero modes of the monopole harmonics on this hemisphere, but there is for a non-trivial R charge, it's known that those zero modes is actually not one zero mode, but the number of zero modes in this background potential actually has a degeneracy. Okay, and M labels the J3. There's some spin, some representation of SU2, of which M labels the J3 eigenvalue. Okay, that's the generator of rotations in the sphere or the hemisphere. Okay. Normally, on a compact sphere, you would have this would be a finite dimensional spin J representation. But in the context of this hemisphere, it turns out that these boundary conditions actually admit an infinite number of these zones. So the representation is infinite dimension. Okay? So I have this infinite amount of Fermi multiplets or 2D chiral multiplets depending on the boundary condition. So I can tell you the full details of this. I realize that this is a bit short, but I had to constrain by time. But there's a detailed, much more detailed stuff. Okay, so then I want to define the hemisphere index in the following way. So schematically, this Hilbert space in the hemisphere times a circle reduces to this infinite product over these two-dimensional Hilbert spaces associated to the multiplets that I have. And I'm going to define an index which takes a trace over this Hilbert space and then weighs the states by these various quantities. Okay, so I'm weighing by the fermion number, I'm weighing by this J, the eigenvalue of this J3, which corresponds to the eigenvalue of the which corresponds to these numbers M. And I'm also going to weigh it by the momentum of the states on the circle, and maybe some other global symmetries that it has. Okay. Now for fixed M, I can interpret this as a 0,2 elliptic genus. But the statement is that this full hemisphere index is sort of a product of an number of these elliptic genera. I put a star here because this is strictly speaking only true for a free chiral multiplet. For gauge theories, you have to be a bit more careful, as has been analyzed in work of energy. Okay, so if I do this evaluation naively, okay, I get an infinite product of these elliptic genera, and I get an expression like this. So I can calculate the elliptic genus of a Fermi multiplet. That is just the partition function of a free left-moving chiral fermion. It's just given by this expression where y, q infinity is the q Kochamer symbol. Okay, and it's a product of these two things corresponding to the left-moving fermion and its complex conjugate. And similarly, for the 2D chiral multiplets, so in the 2D chiral multiplets, the only left-moving states are given by the bosons. Those are the elements that contribute to the index, and I get this form for the hemisphere. Okay. Now, there's an issue with this expression, which is related to that I'm trying to calculate an index for an infinite number of multiples. Okay. So this is actually divergent for any complex value of p. The reason for that is that I have arbitrarily positive and negative eigenvalues for this J-free eigenvalue. Okay. So that is a problem. But there is a fix. There's sort of this problem also suggests a fix, and the fix is as follows. So I want to make these indices convergent. I want to basically only include either positive or either negative J-freedoms. In that case, I will have a convergent expression. And the way to do that is to impose opposite boundary conditions on the chiral and the anti-chiral. Okay? That takes out from the chiral state a positive J-freedoms, and from the anti-chiral also the positive J-freedoms. Okay? So I get this sort of, if I impose boundary conditions like this, I get contributions, say, from the left-moving fermion and a left-moving boson. But I'm forgetting about the complex conjugates. Okay, so that's sort of the fix that I impose by hand. And when I impose that fix, I precisely obtain. I get something convergent. So I get here you see the contributions of the fermion to the 2D left-moving fermion and the 2D left-moving boson. And there's an infinite amount of them, but in this case, because P has a positive power for both these cases, I actually get something convergent, and it is precisely this elliptic gamma function. This confirms this. So this prescription confirms my first claim, namely that this factorized expression for the index can be interpreted in these terms of these hemispheres. So this index is precisely one of these factors that I wrote down all the way in the beginning when I took the trace over this Hilbert space factorized into negative J2. Okay. So what is the picture here? The picture is somehow that in terms of this single letter Hilbert space, okay, the two-dimensional picture of this single letter Hilbert space is that as I move along the diagonal, I label which 2D multiplet I'm looking at, and then either if I go the states that go on top of that, or vertically on top, or horizontally to the right, correspond to the descendants of these multiplets that contribute to the elliptic genus. Okay. So that gives us an identification of the momentum along the circle corresponding to the J2 quantum number of the states of this space, and J free, the generator of rotations, is given by the quantum number associated with either capital J2 or capital J1, depending on whether northern or southern hemisphere. So the intuitive picture of what is going on really here is that the separation of the Hilbert space into states with either J1 larger than J2 or J1 smaller than J2, I can think of these, the wave functions associated to the states as sort of separating along the base of the Hopf vibration. So these wave functions in particular, depending on these, on whether these charges are larger or smaller, attain their maximum on either side of the sphere. Okay, so that's sort of the intuitive picture behind this geometric interpretation of this factorization. This is actually consistent with a relation of N=2 SCFTs with chiral algebras, which can be thought of in this picture as sort of living at the pole of the base. Okay, I think I'm probably out of time. So let me just get to the statement of modularity. So the idea is that I can perform a modular, so I have this factorization in terms of hemisphere indices, which can be thought of as an infinite product of these 2D elliptic genera associated with either the northern or the southern hemisphere. And I can figure out how modular transformations that act on the torus act on these chemical potentials that I've inserted here. Turns out they act as such. So this is sort of the prediction from the picture that I've been proposing. This is the modular property this is the modular property. And this property can be proved in the context of the free color. So the elliptic gamma function precisely satisfies a property that allows you to prove a statement like this.
Why do you have question mark equal to?
Yeah, so it's not quite equal to. There is a phase that sits in between. But that's sort of a bit similar to how Jacobi forms are not quite invariant under modular action, but they're invariant up to a phase. Modular program.
So what happened to your argument? I thought you had an argument that the index would be. So what went wrong with the argument? The argument
So that's
is
the usual. That's I think I haven't pinpointed that quite, but that's the usual thing that goes wrong if you try to translate Hamiltonian to the Lagrangian picture. So so for the elliptic genus, there was a similar argument where the trace formulation of the elliptic genus is not quite equal to the path integral, but there's some factor of proportionality that precisely cancels how the trace is covariant, whereas the full path integral is manifested.
So I didn't understand that. I thought the trace is the path integral. Why is it not?
No, it's the path integral up to a phase. That's for a supersymmetric prediction for these indices that is
You do S3 cross S1. You do path integral on S3 cross S1. That is the trace. Why is it not the trace with the right boundary conditions on the S1?
Yeah.
You're saying this phase is somehow coming from there.
Yeah, there is a phase in this context. It's known as a supersymmetric Casimir energy. There is a prefect. There is a prefect up to which these things match.
I mean, is there some
This
anomaly
is
in
a
the
known
path?
thing in
Yeah,
dimension.
usually there's a gravitational anomaly which is
Is there?
reflected in the modular anomaly.
I
Is
think
this, maybe there's an anomaly. You're saying.
there is an anomaly. That's
But then you should be able to trace the anomaly, right? There's
Yes.
some change in the measure which is not valid.
yes. That's true.
So this factor must satisfy some consistency condition, right? This phase factor that you showed,
Yeah.
that if you get two successive transformations, it transforms appropriately.
Yeah,
Phase
well,
factor.
it's a little bit more trickier in the sense you see that the modular transformation is a bit funny in the sense that, so I have these two factors, and it's really the combined modular transformation that which has this invariance. Actually, Abhijit has proposed a consistency condition on this phase, and this should be consistent with his consistency condition. It's analogous, but not quite the same to this one cosine condition. So Abhijit proposed that it's actually a two cosine.
Yeah, 2%.
I haven't fully checked how it fits with this. I think that's all. That's the.
More questions?
Yeah, maybe a more general question. So it seems like quite a lot of things have to conspire in this case so that you could get some echo of modularity.
Yeah.
Do you think that this is just special, or do you see ways that this could be generalizing?
So I think it can be generalized to higher dimensions. For example, it can be. I think it also can be generalized to other superconformal field theories. Yeah, maybe. So yeah, my claim is that it's not very special to this field. I can explain that.
Other questions? But in particular, can you also do here you do three split, right? S1 times S3,
Yeah.
do then S2 times S2. It's like a Euclidean
Yeah.
number engine. I mean, it is Euclidean.
Yeah. And then, so what I've been relying on somehow here is this trace formulation where I have a nice factorization of the Hilbert space. Perhaps when just looking at that, something can be said about those more general cases. But yeah, my tool here has been really be applied, I think, to this.
Maybe again, I'm still looking the geometrical significance of sigma and tau.
Yeah, that's what I haven't talked about it all, but
Like some small circles become a big circle, right? When you're doing this.
yeah. Let me see. Yeah. So when you in sort of a Lagrangian point of view, the index can be thought of as a path integral on S3 plus S1, where these chemical potentials become moduli, can be understood as moduli of the geometric background. It's what's known as a Hopf surface. And this separation into hemispheres gives me sort of this hemisphere times a torus. And if you carefully do that, you find that the complex structure moduli sort of translate into moduli of the tori that arise in the spittle. And one of these tori has complex structure modulus tau, the other torus in the southern hemisphere has complex structure modulus sigma. And so the claim is that this torus, on which I'm doing the SL2Z transformation, is sort of topologically the Hopf fiber times the temporal circle, but it's sort of fibered non-trivially over this polar angle, and in particular its complex structure modulus changes continuously from tau to sigma as I go from the northern to the southern hemisphere. And otherwise, the SL2Z transformations that are performed on this torus just act in a normal way on these complex structure moduli. So in particular, exchange large and small circles. So if my Hopf fiber, let's say, is small and my temporal circle is large, if I do the S transformation, then this in the standard way exchanges these.
But you cannot independently transform tau independently because they are linked.
Yeah, they are linked to the same torus. That's right. So they're linked to the same torus, so that's why I have to do basically the same transformation. In fact, if you carefully follow this through, it's very natural. It seems to be very natural to take a specialization of sigma, to take it to be minus the complex conjugate. In that case, you can figure out that the SL2Z transformation precisely X the same on top, tau on top of it as it's supposed to be. But that's something that so it suggests a bit that this modular factorization, perhaps in some limited specialization, can be understood as a type of holomorphic anti-holomorphic factorization. But there's some details that don't quite make it the same as intuitive. But that's something that I'm still working on.
Okay, thanks, Sam. Let's take a 5-minute break.